Hi friends, in today's class we will discuss the stress versus strain diagram of a mild steel specimen when it is conducted tensile test, and we will come across different points on that curve. Let us discuss. Suppose we are having a specimen. We are having a tensile test specimen. Let this is the specimen. Now we will use this specimen. We will put this specimen in machine. Let that is UTM machine, universal testing machine, and we will conduct tensile test by that machine. Suppose there is a machine. This machine is having, let this is upper jaw, this is lower jaw, and we will put that tensile test specimen here. Now there will be, now we will apply the force. If we will apply the force, it is subjected to tensile force. That means, let this is the specimen. If we are applying the force, tensile force will act. Then we will increase the load. Gradually we will increase the load. The body will elongate. That means strain will be there. So after some time, when it can't resist, it will fail. That means at certain point the body will break. So we will find out different points on the curve during this test. So after the conduction of this test, we will get a curve somewhat like this. Let's see. We will plot stress versus strain diagram, and the curve maybe we get like this. So let us notate different points. Let this is A, this one is B, this is C, D, and this one let it is A. Now this point is, A is known as elastic limit, B is known as upper yield point, C is known as lower yield point, point D is known as ultimate point, and E is known as breaking point. How the point will occur? Let us discuss. So due to this application of tensile force, where we are applying the force, tensile force will act or not. So a certain stage will be there, a certain point will be there. If we remove the load before that point, before that application of that force, then the body will regain its original shape. That means, suppose we are having a body like this, and up to point A, let we are applying 10 kilonewton. After 10 kilonewton, it will go to this region, leg. So let this point will occur 10 kilonewton. Suppose I am applying 8 kilonewton here at this point. If after application of 8 kilonewton, let the body will elongate somewhat little more than that. Now at this stage, I will remove the load. At 8 kilonewton, I will remove the load. Then the body will regain its original shape and size. It will come back to its original shape if I remove the load. So up to this point, whenever I will remove the load, it will regain its original shape. So this point is known as elastic limit, and beyond that point, if I remove the load, it will never gain its original shape and size, and that is known as yielding zone. What is yielding zone? Now this, in yielding zone, without application of any more force, if suppose we are not applying the force but strain will be there, that means the change in length will occur without application of force. Generally we know, if we will apply the force, there will be change in length, but in this zone, yielding zone, without application of force also, it will elongate. This zone is known as yielding zone. Remember, if the body will comes under yielding zone, it will never gain its original shape and size. That means it comes under plastic region. Then if you add on some more force, then an ultimate stress will develop, that is at point E. Then after some time, breaking point will occur. The body will break. That means up to point A, stress is directly proportional to strain. If stress will increase, linearly it will vary, strain will vary. That means stress is directly proportional to strain. And Hooke's law applies here. Hooke's law obeys here. So up to point A, up to elastic limit, it obeys Hooke's law. That means stress is directly proportional to strain. Then after that, yielding zone. So this is all about different silent points of this curve, stress versus strain diagram. Whenever we are putting a mild steel on a machine, and we'll conduct the tensile test. So during the tensile test, we'll get the curve like this. Suppose we are having cast iron or a rigid body, that is glass material. So for glass material, how we will get the stress versus strain diagram? We know there is very little deformation will occur. Suppose glass material is there, and I am applying the force without any elongation, it will break. That means there is small change in length, then body will fail. That means it obeys Hooke's law. Then after some time it will break. The curve will remain like this. For rubber materials, we are using the eraser for erasing purpose. For rubber material, the stress versus strain diagram may be like this. You can't differentiate the yielding zone. If you magnify this point again and again, magnify, still you will not get any. You can't differentiate the yielding zone. So this is all about stress versus strain diagram of different material, and this one is for your mild steel specimen. And there is a difference between elastic limit and proportional limit. So there is elastic limit. Before that, we will reach a point. Let that is A dash. This is known as proportional limit. That means exactly stress is directly proportional to strain up to A dash. Then immediately we will get elastic limit. If we will approach macroscopic, then we will take point A. If you go for microscopic level, microscopic studies, then for proportional limit, up to proportional limit, Hooke's law obeys good up to point A dash. But if you approach macroscopic, then you can consider point A. Up to elastic limit, it obeys Hooke's law. So this is all about stress versus strain diagram. In next video, we will cover some other things. Thanks for watching this video.